In previous video, we discussed that we use bandpass filter here to generate the single sideband AM signals. Like here, we use a bandpass filter to filter out the upper sideband signals. And of course, if we modify the bandpass filter, we can filter out the lower sideband portion. Here, that's the filter to filter out the upper sideband signal. We can see this is single sideband modulated signal. The diagram of using bandpass filter to generate single sideband signals can be expressed in this figure. We have the message, we multiply by the carrier, and up to this point is DSB SC signals, and then we pass through the signal into bandpass filter. Depending on the cutoff frequency, we can either have upper sideband or lower sideband. So we generate the single sideband signal using the bandpass filter. However, the drawback is the requirement ideal bandpass filter. By ideal filter, we mean that at FC, the response of this filter has to be 1 immediately. But in practice, we normally get this and gradually go up and gradually come down. That's what we normally obtained in real filter system. An ideal filter like this, cut off here and cut off here, is very, very hard to obtain. Another alternative to generate the single sideband signal is to use Hilbert transform. The modulated signal contains two parts. The first portion is the DSB-SC signals, because that's the message multiplied by the carrier. The second portion is the Hilbert transform M hat. That's the Hilbert transform of the message, and we multiply by sine 2 pi of CT with the same magnitude, and we take the difference. This modulated signal will generate the upper sideband signal for single sideband transmission. If we want to transmit the lower sideband, we take the plus on this portion. The diagram to implement this, I draw it here. We got a message. We multiply by the AC cosine 2 pi of C. And now we do Hilbert transform. We multiply by AC sine. And from here to here, we can use 90-degree phase shift. We can obtain this sine signal. And after we obtain those, I use adder. And then I can obtain the upper sideband USB. And if I take the difference, I will obtain the lower sideband. Next, we look at the frequency domain of the modulated signal. This portion is DSB-SC. We know what it looks like in frequency domain. We only need to focus on this term. Now let's look at the Hilbert transform. The definition of Hilbert transform is convolution. The message convolute 1 over pi t. I can write the Hilbert transform as g of t convolute mt. Then g of t equals to 1 over pi of t. We know that if we have convolution in time domain, we will have product in frequency domain. That's exactly here. So we need to obtain the Fourier transform of g of t. G of t is 1 over pi t. So we really need to find the Fourier transform of 1 over pi t. Let's look at one popular Fourier transform pair. We want to use this Fourier transform pair. Now I write it here, sine t Fourier transform is 1 over j pi f. Next, we want to use duality, x minus t, or corresponding to small x f. In this case, what is a big x minus t? That equals to, this is a big x, we want to replace f with minus t. So j pi minus t. Now what is xf? You want to replace this small x t, this is small x t, with f. So therefore that's sine f. Therefore we can see that 1 over j pi minus t Fourier transform is sine f. And then you move this minus sign to the other side. Fourier transform is minus sine. Remember that we need to evaluate the spectrum for this term. We want to use this property and Euler's formula. This is Euler's formula we need to use. I wrote it here as well. Now we replace x with 2 pi of ct. This is what we have from the Euler's formula. From the frequency shifting property, xt, if time domain multiplied by complex exponential, e to the power j 2 pi of c, then the spectrum just move to fc. This is the amount. Pay attention, this is amount fc, and this is fc. If we multiply the time domain by the e to the power minus j 2 pi of c, really here is this is e to the power j 2 pi minus fc t. The spectrum shifting to minus fc. So therefore we can see xt, if I multiply by 2 pi of ct, that equals to half 2j sin xt e to the power j 2 pi c of t minus xt e to the power minus 2 pi of c of t. Right? The Fourier transform of xt sine 2 pi of ct. And remember, I take this minus sign out first. I take this minus sign here. So therefore, this portion is corresponding to f plus fc, this term. This portion corresponding to f minus fc, that's here. Now we replace xt with minus m hat t. So minus disappeared here. Big X becomes big M hat. And what is M hat? That's equals to minus J sine F multiplied by MF. And this comes from here, the derivation. This is what derived here. The Fourier transform of 1 over J pi t. The Fourier transform is minus sine F. So therefore 1 over pi t, the Fourier transform, we move j on this side. The Fourier transform Hilbert is gf multiplied by mf. Gf, that's the Fourier transform 1 over pi t here. So therefore we have this. I wrote it here as well. And then plug this in. Now let's look at this term. This is as a positive frequency here. Sine f has this shape. This 0, that's 1, that's minus 1, right? So this is sine f. So sine f shift to fc. So everything shift to fc. I plot it here. Here I plot it here. And this is 1, this is minus 1. F minus fc, term of mf shift to fc. So here that's fc as ms. So this multiplied together, these two terms multiplied together, draw it here, and this is fc. So I move this portion up to here. We line up frequency and we multiply the values to function together. So on this side, this is 1 multiplied by everything. That's this portion. And on this side, everything multiplied by -1. Value at 1 becomes -1. And here half becomes -half. And 0 is still 0. So that's the shape of this two waveforms multiplied together. That's this. That's this waveform. Similarly, we can look at the negative frequency here. F plus FC is shifting to minus FC here. And then this is a minus sine F plus FC. And this is this term, this is a sine F, move to minus FC and multiply by -1. So you flip the value. There's a minus sign here. You have 1 on this side and -1 on this side. And then when you multiply this together, and this portion, that's this portion, and this portion is multiplied by -1. That's this portion. So at this point, we look at the spectrum of this term. Now the spectrum of U of T, we need to add the spectrum of DSB-SC. That's this term. Now I plot the DSB-SC spectrum. So this is DSB-SC. Remember here I didn't mark, but we want to look at the shape of the spectrum first. And let's look at the positive frequency. This portion is come from the Hilbert transform term. If we add this together, because this first term is DSB-SC term, the second term, that's this term is Hilbert transform term, we need to add them together. So this is FC, and this is FC as well. And we can see the lower sideband signal. This is the lower sideband. This is the lower sideband. And this is positive, this is negative, being cancelled out each other. What we left out the upper sideband. And this is a positive frequency. Let's look at the negative frequency. This is a negative frequency. Everything shifted to minus FC. This is a minus FC. So we add them together. This term is come from DSB-SC term, and this term is the Hilbert transform term. For the lower sideband, positive portion and negative portion, they cancel out each other. What we left out, that's this portion. This portion and this portion. So that's the upper sideband. If we combine them together as a positive frequency, we obtain the upper sideband modulation. Mathematically, the expression of the spectrum of the upper sideband modulation is we take this portion, we can see this portion is the DSB-SC expression only when absolute value of F greater than FC. In other words, when F greater than FC in a positive frequency, or F less than minus FC when the frequency is negative, and rest of frequency we take a 0, that's here. And this is the mathematical expression for the spectrum of the upper side modulation. Because the single sideband only transmits either the upper sideband or the lower sideband, the bandwidth of the modulated signal is the same as the bandwidth of the message. And the power is a half of the DSB-SC signal. This is the power for DSB-SC signal. We take another half, that becomes AC squared divided by 4 PM, and PM, that's the message power.